In previous video, we discussed about the basics of problem table algorithm, why problem table algorithm came into existence, what are the limitations of plotting the composite curves, and how do we implement problem table algorithm. So what is the principle behind that? So for performing analysis through problem table algorithm, we first need to define delta T minimum. This delta T minimum will give you an idea about the energy targets, and this will help you to shift your temperature for hot and cold streams. The shifting of temperature is done to make sure that any given time, right, your hot stream and cold stream temperature are away from each other by minimum delta T difference. So what do we do? How do we shift the temperature? So, to shift the temperature, we subtract delta T minimum by 2 from the hot stream and add delta T minimum by 2 to the cold stream. That means we are making our hot stream colder by delta T minimum by 2 and the cold stream hotter by delta T minimum by 2. So actually, when I convert the shifted temperature to the actual temperature, what happens is that at a given temperature, if I have a hot stream, actually the hot stream is delta T minimum by 2 hotter by that value, and cold stream is delta T minimum by 2 colder by that stream. So automatically the difference between the two stream would be maintained as delta T minimum, right? So this we'll see as we proceed further, right? And this is the problem statement which is there in front of us. Say there are four streams, one is cold, like number 1 and 3 are cold streams and 2 and 4 are hot streams. Their CPs are respectively 2, 3, 4 and 1.5. Their supply and target temperature for stream number 1 is 20 to 135, stream number 2 170 to 60, stream number 4 80 to 140, and stream number 3 80 to 140, and 4 is 150 to 30. Now when we want to shift the temperature, what do we do? For cold stream, as mentioned, we add delta T minimum by 2 to supply and target temperature. So since delta T minimum is 10, delta T minimum by 2 becomes 5 degree, and this becomes 25 and 140. In the same way, for this cold stream it becomes 85 and 145. For hot stream, we subtract delta T minimum by 2, and hence 170 would get converted into 165 and 60 would get converted into 55 for stream number 2, and for stream number 4 150 gets converted into 145 and 30 gets converted into 25. So this shifted temperatures will give you the range of the temperatures. Now this needs to be listed vertically in the decreasing order. That is, we start with 165, then we put 145. Since there are two entries for 145, we will consider only one entry for 155, then 140, then 85, then 55, and then 25. Right. Now for every temperature interval, we calculate the value of delta H associated with that particular interval. So say for example, I have an interval I wherein the temperature difference is between 165 and 145. So I will just find out the number of streams available in that particular interval, and then for all hot stream associated within that interval stream, I'll make the summation of heat capacity, and for all the cold stream available in that particular interval, I'll make summation and take the difference of this. So what I mean to say is this. So say for example, between these are the interval 165, 145, 140, 85, 55, and 25. Now between 140 and 145, I have stream number 3, stream number 4, and stream number 2. Right? Stream number 3, right, runs from 80 to 140. Stream number 4 goes from 150 to 30, and stream number 2 goes from 170 to 60. That means these two streams, stream number 2 and 4, are hot streams. Right? So for hot streams, right, I will calculate the CP for stream number 4 and that for stream number 2. So what are the CP values? CP values for stream number 4 and 2 are 1.5 and 3 respectively. So my CP hot summation is 4.5, and stream number 3 is available in this 140 to 145 interval. So for stream number 3, the CP value is 4. That means if I make the summation of 4.3 plus 1.5 minus 4, making the value of delta of CPH minus CPC to be 0.5. Delta T or SI minus SI plus 1 will become 145 minus 140, making it 5. So for every interval, I'll find out delta H by multiplying the temperature difference with the heat capacity summation difference of hot minus that of cold. So first my job is to list the temperature, then identify the streams which are falling within individual interval, and for every interval I'll find out delta H. So how do I do that? This is my table shifted temperatures. I will list the temperature like this: 165, 145, 140, 85, 55 and 25. Then I'll write interval number. So this is first interval, second interval, third interval, fourth and fifth interval. Now for every interval, what is the delta T? So delta T is 165 minus 145, making it 20, 145 minus 140, making it 5, 140 minus 85, making it 55, 85 minus 55, making 30, 55 minus 25, 30. So this is delta T for the corresponding interval. Now I'll find out CPH, summation CPH minus summation CPC. So for interval 1, since there is only one stream available, which is a hot stream, so I'll consider that as plus 3. Stream number 2, we evaluated 3 plus 1.5, so stream number 2 and 4 were present, minus that of cold stream number 3 available, so 3 plus 1.5 making it 4.5 minus 4 making it 0.5. Again, let us check for interval between 3 and 4. So how many streams are there between 3 and 4? Let us see. Between this, the stream available are all the 4. Right, all the 4 streams are available. That is stream number 3, stream number 1, stream number 4 and 2. So what I just need to do is, for this I have to add the CP values for hot, that is 3 plus 1.5, 4.5 minus 4 plus 2, 6, 4.5 minus 6 making it minus 1.5. Likewise for this interval and for this interval. Now the next step is find out delta H value. So delta H value is nothing but the product of these two columns or the elements of these two columns. So 20 into 3, 5 into 0.5, 55 into 1.5, likewise. So this becomes my enthalpy associated with every interval. So 60 kilowatt is the enthalpy associated with interval 1. 2.5 kilowatt is the enthalpy associated with interval 2, minus 82.5 is enthalpy associated with interval number 3, plus 75 is associated with interval 4, and minus 15 with between 4 and 5, that is 5. So every plus is a surplus. That means that much amount of energy this particular interval can pass on to the next interval which is lying at a lesser temperature. And minus 82.5 means this much amount of energy this particular interval requires. You can see that we have 75 kilowatt of energy just below minus 82.5. It is here. But can I transfer this from here to here? The answer is no. The reason is that this energy is available to me at a lower temperature than this. So the transfer of energy or the direction of the transfer of energy will be always from the higher interval to the higher temperature to the lower temperature. Now let's say these are the surplus, right, and deficit ratio. So this is what I said, that any as such all the surplus can transfer heat to cold utility and any deficit can be supplied with hot utility. So I can do that. I can directly give minus 82.5 here and I can pass on that till the last interval and then that can go to cold utility. But any heat available in interval I is hot enough to supply any duty in interval I plus 1. That means I can supply this here, 2.5 I can always supply. Right, so I can always transfer heat like this or I can use utility. So it is possible to set up a heat cascade as shown below. So the first heat cascade which I have shown is like, say for example, I don't supply any hot utility. That is, I just let the 60 kilowatt in interval 1 remains as it is and I transfer it to the second interval. So 60 is passed on to the second interval making this to be 62.5. 62.5 passed on to the third interval making the flow as minus 20 kilowatt. If somehow I'm able to pass it on to the next interval, then it becomes 55 kilowatt, because minus 20 plus 75 making it 55, and this 55 when it transferred to the last interval making it 40 kilowatt. So this means that I don't need any hot utility, I just need 40 kilowatt cold utility. However, what I need to check here is that this minus 20 kilowatt, that means I have supplied 20 kilowatt of energy from interval 4 to 3, which is against the law of thermodynamics. So how do I correct this? To correct this, what I need to do is I need to supply minimum, right? Minimum 20 kilowatt as a hot utility on top. The moment I supply that 20 kilowatt here, my entire heat balance would be like this: 20 kilowatt plus 60 making it 80, plus 2.5 making is 82.5, plus minus 82.5 making it 0, plus 75 making it 75 kilowatt, minus 15 kilowatt making it 60 kilowatt. That means what? I can transfer energy from top to bottom with 20 kilowatt of hot utility and 60 kilowatt of cold utility. How do I analyze this particular? So it is possible that in this particular cascade, this minus 20 kilowatt is coming between interval 3 and 4. Now this can come here, this can come here, and the value could be anything other than minus 20. So what we need to do is we need to analyze this particular cascade, and we have to find out the highest value of negative heat transfer. That means if I got minus 62.5, then what I'll do is I'll supply 62.5 kilowatt here. If I got minus 70 kilowatt here, I would supply 70, because the moment I take care of the highest possible negative value, the remaining values would be taken care of automatically. It is also possible theoretically that your highest negative value may come here. In that case, what you need is you need only hot utility, and the cold utility requirement is 0, because when this is the highest value, you supply that, and when you keep on passing these values, this will become 0. The other possibility is when you supply no hot utility, not a single value will come negative. If there is no single value which is coming out to be negative, that means it is a feasible cascade and you don't need hot utility. What you need is only a cold utility. Fine. So let us try to see this graphically. So this is your cold stream and this is your hot stream, right? If there is no hot utility, it is quite possible that you have an overlap, and this overlap is maximum here. So what you try to do is you try to minimize this overlap and shift this curve to this point. This is a shifted temperature, mind well. So when they are touching each other, their actual temperature difference is delta T minimum. How do you do that? By supplying utility here. So if you supply utility here at this place, the curve which was overlapping has moved down here. So this is the actual temperature value, and dotted lines are your shifted temperature. So that is what happens by supplying the deficit heat on top. Few things to be noted. There are three ways of moving the hot and cold composite curve closer together by delta T minimum, so they touch at a point. So there are three ways you can shift the temperature. We started off with saying we make hot stream colder by delta T minimum by 2 and cold stream hotter by delta T minimum by 2. But the other two ways which we can do is express all temperature in terms of the hot stream temperature. So keep hot stream temperature as it is and increase all cold stream temperatures by delta T minimum. Eventually, when you come at a pinch point, the hot stream temperature remains same, but cold stream temperature would actually be cold stream temperature shifted minus that of delta T minimum. So eventually the difference would come out to be delta T minimum. In the same way, you can express all temperature in terms of cold stream and make your hot stream temperature reduced by delta T minimum, right? And the third is what we discussed here, which is the most prevalent, that you change both hot and cold stream temperature. Hot stream reduce temperature by delta T minimum by 2 and cold stream increase the temperature by delta T minimum by 2. In either of the cases, right, your answers would not change. The thing we are shifting the temperature is to make sure that any given time there is no overlap and your temperature difference between the two streams is maintained at delta T minimum by delta T minimum, correct? So with this I think we end here, and when we meet next time we'll talk